Hi, so I'm Jason Dworkin. I'm the project scientist for OSIRIS-REx. OSIRIS-REx is a robotic spacecraft, part of the New Frontiers 3 line. The principal investigator, Professor Dante Loretta, University of Arizona. It is, like I said, a robotic spacecraft, artistically rendered in Legos. Its purpose is to get a sample of the asteroid Bennu, which is a near-Earth asteroid, a very primitive, ancient piece of rock, and then bring it back to the Earth. Right now, it's unfortunately a little dull. OSIRIS-REx is orbiting asteroid Bennu. It's a very small asteroid, half kilometer across, sort of spherical-ish shaped. And right now it's in a very low orbit, 0.7 kilometers from the surface. This is, we previously broke the world's record twice for the slowest, closest orbit the spacecraft on any object. Right now, you can't see Bennu because the spacecraft is currently downwind from the high band antennas pointed at Earth. We're getting recently collected data. What the spacecraft is doing orbiting to get ready to do another low flyby of our top sampling sites. The purpose of OSIRIS-REx is to get a piece of asteroid to the Earth to study in laboratories around the world to understand ancient primitive material that led to the formation of planets, perhaps the formation of life. But we need to find a site that is safe and we can get a sample of. We've down selected to our top site with the backup. The top site is called Nightingale. It's about here. And you can, oh yeah, this is the orbit right now. We're in Recon B 625 is the nominal orbit. Right now it's 0.7, depends on if it's apoapsis or periapsis. This is, we can find all this information at asteroidmission.org. You learn more about it.
How was this asteroid chosen?
Very good. So there are 750,000 asteroids. At the time of the mission selection, this was a competitive mission. There are only 500,000 asteroids known. We had to pick one that we could get a spacecraft to and back from within the lifespan of the science team. That's the first requirement, which means we need to go to near-Earth asteroids as opposed to the main asteroid belt. Next, we need an asteroid that we can get to and back within the propulsion systems available to us, having a low enough delta V. Bennu has a orbital inclination of only 6 degrees, and so we can leave Earth and do an Earth gravity assist and get to Bennu and then back again. Of those, we needed an asteroid that was larger than 25 meters in diameter, because smaller than that, asteroids tend to spin really fast. They tend to spin up to 1 revolution per minute. And so that leads to two problems. One is, as asteroids spin faster, the loose regolith we're trying to pick up flies off into space and is lost. Also, what we need to do is map the rotation speed to do the touch. And so if it's rotating that fast, the navigators have a lot of trouble maneuvering the spacecraft, because remember, this isn't fly-by-wire. There's a 18-minute lag time between, from light, between what you send a command and what the spacecraft does. So it all has to be robotically programmed. Of those, we wanted one that was primitive, that had spectra consistent with a loose, ancient rubble pile. In this case, this is the Class B asteroid, reminiscent of carbonaceous chondrites, such as this one. This is a piece of the Allende meteorite. That's the oldest thing you ever touch. The little white letters in there are 4.576 billion years old. That's older than the Earth.
So you guys are touching a really old spacecraft.
Yep. Landed in the next one, 1969, though. And of those, we needed an asteroid that we could understand very well. And so the top choice was Bennu. The number two choice, by the way, was Ryugu, which was the target of the Hayabusa 2 spacecraft. We'll be able to compare the results of those two. And so, in fact, we were quite accurate. We used the Arecibo and Goldstone radio telescopes to get radar maps of Bennu. This was the pre-launch radar map we got, and then this is after that encounter. Really, really good. The little things here are the actual pixels. Now you can't see the pixels because the printers don't have that resolution. We're now down to 21 centimeter per pixel on this. On this, we're down to 1.8 centimeters per pixel, and then at our next flyby, we'll be down to less than half a centimeter per pixel. So we'll be able to really understand in great detail where our sample came from. You see, meteorites land on the Earth all the time, like these. Again, the primitive carbonaceous one, the ones you usually see in museums. This is a piece of QapkOf yellow with the Wickman-Schatten pattern you can see from an acid etch. It's nice and heavy, which means that it's easy to pick up, easy to notice because magnets are attracted to it. Unlike carbonaceous chondrites, which are more primitive but harder to notice because they look like rocks unless you're being very, very careful. Pontificating about.
How asteroids are chosen?
Right. Well, yeah. So we picked the one that was that we knew the best, had evidence of being primitive, like the carbonaceous chondrites, and we could get to. We have these articulated solar arrays, and that's actually really important because this is such a small asteroid that the solar pressures are on the same order of magnitude as the force of gravity when we're in these close orbits. So we need to maintain the same center of pressure and center of mass on the spacecraft. That also allows us to do nicer camera angles than Hayabusa 2 was able to do because they have fixed antennas, but still, fantastic mission. Anyway, so the way the spacecraft works is when it's time to do our sampling on Nightingale, which is here sort of parking lot sized. Oh yeah, there's why. The spacecraft is better built than Legos. The spacecraft brings its solar arrays up like this, so that as it comes down to touch the surface, in case it tips, it won't touch the ground. It has this 3-meter long pogo stick on the bottom that on the end of it has a device that looks kind of like this, the PAGSEN head. It's 21 centimeters across. Coincidentally, that's the same resolution as the global shape map of the asteroid, for obvious reasons. The spacecraft does a free fall from 25 meters, that takes half an hour. Touch the surface. This is a pogo stick, so the springs bounce. As that's happening, we fire a jet of nitrogen gas. The jet on the head stirs up the regolith, like I'm demonstrating in a moment, collects a minimum of 60 grams, as much as 2 kilograms of surface regolith. Comes back up. We measure the weight by seeing the change in moment of inertia, and then stow it in the sample return capsule and send that back to Earth. In 2023, September 24th, around just before 9 a.m. Mountain Standard Time, Mountain Daylight Time, the spacecraft ejects the sample return capsule, does a divert maneuver away from the Earth. Sample return capsule lands in Utah.
What's the date?
September 24th, 2023. It's a Sunday. Within 2 days for rapid analysis, cataloging, and then open up to the global scientific community after 6 months. The best thing I like about sample return missions it's not constrained by the wonderful payload we have on board, the cameras and instruments. It's constrained by the ingenuity of the scientists on Earth and the machines that they may not have invented yet, the ideas that they may not have come up with yet. So for example, one of the laboratories you went to, they're studying lunar material that was actually sealed and then opened up 50 years after it was collected, being analyzed by scientists who are not yet born when the samples were collected, answering questions that were unanswerable in the 1970s on instruments not yet invented. This is spectacular. South Trek do the same thing. 75% of the samples reserved for future generations. And scientists outside the science team. Anyone can anyone who can demonstrate the ability can write a proposal and get samples. This is a toy version of it. It's a little container. It has these contact pads on the bottom as a backup opportunity. It is literally Velcro, but made out of stainless steel. And that captures little particles. And then, I've never done this before, we'll see how it works. You shoot a jet of nitrogen gas, and dust flies up, and then we can get it back to Earth and see how many goodies we got in a more careful manner than that. And I should have tared my balance first to see what we got in that little demonstration. So that's 45 grams minus 25 grams. So that was 20 grams of seeds from a quick low pressure jolt of this is nitrogen, but whatever. So we used 3,000 psi nitrogen to do a 5-second blast of nitrogen gas, collected the sample. We've tested this at microgravity, under vacuum, different temperatures, all kinds of other scenarios to understand how this works, and we always get at least 150 grams. The requirement is 60, the best is 2 kilograms. I'm a scientist, I always want more. More is better.
How old is this, you said?
The little white irregular blebs are called calcium aluminum inclusions. That's the oldest solid in the solar system. Those are 4.567 billion years old. The chondrules are a little bit younger, melted by a process we don't understand. We hope to learn more when we get Bennu back. And the black matrix, those are made of phyllosilicates and clays. Much like Bennu has, we see evidence of water over the entire surface, down to clays. We also see, the other thing I forgot to mention that was really surprising is Bennu is spitting at us, or not at us, but in general. Particle ejections are happening. The latest one was we saw 600 particles shoot off the asteroid. Some go into orbit, some are lost, some come back down. One was stable for several days, come back down again. So there may be, in the southern hemisphere in September, a Bennu meteor shower. We have observers looking for those, now trying to identify meteor shower consistency. And so, in all probability, there's Bennu samples on the Earth, we just don't know what they look like. Or maybe they're so friable, so loose, because the thermal inertia isn't what we thought it was, that they don't survive with the entry of the Earth. So making this a truly unique sample.
It's a dam. They're fighting. It's a cool hotel. He's Hollywood star now. It's all different world here. Fighting each other. Beautiful coastline. Miles and miles and miles. Here is how I did 10 days road trip. I will be flying over from Washington DC to Colorado.